I hope you guys had a good long weekend and had a chance to relax. If you were needing some time to get caught up and you used this opportunity to get caught up, please make sure that you reach out to me to let me know to look for things so that way I can get your grades updated accordingly. We're going to continue working on the mole, so we're kind of on our fourth concept. And so we started out with how to convert particles, whether it be atoms or molecules, to moles, and then grams to moles using molar mass. Today we're going to connect the two. So if you haven't done so already, what I would recommend that you do, and I've got this posted to today's assignment, is that this is a road map. And so this is really useful in that, like a map, it gives you directions on what to do based on what information you're given. So today we're going to connect. And so we've done this bottom two halves, but like I said, today we're going to connect these two pieces into one big conversion. We've done them as two separate pieces. So how you can get this, you can either print it out, you can snap a picture of this, you can sketch it out on a piece of paper. It doesn't have to be super fancy, but like I said, whatever works for you works for me, and this is going to be really useful as we continue to move forward in working with the concept of the mole. So I only have two examples. I'm not going to have a lot of examples for today because you have that roadmap, and like I said, it's just bridging two pieces together. If you are needing more examples, more help, reach out to me through Google Hangouts and email, and I will get back to you. So today in our first example, it says we have a 10-pound bag of sugar. It contains 4,536 grams of sucrose. So chemically, sugar, like table salt of sodium chloride, sugar is made out of sucrose, and it's C12H22O11. It asks how many molecules are present. Well, the first thing is that 10 pounds is irrelevant information. It's not necessary for solving the problem. What we do need is our given. So it's mass. We're starting with grams of this sucrose. And what they want to know about it is how many molecules. So we know that with molecules, we need Avogadro's number. And then when we have mass, we know we need molar mass. Well, we know that different elements and different compounds have different molar masses because of the composition being different. So we don't have a direct conversion that can take grams to molecules and vice versa because they have different masses. So what we have to do here, and if you go and look at your roadmap, the middleman is the mole. So it's kind of like two-step metric conversions. You have to convert to the mole, and then you can go to any other particle using that appropriate conversion factor. So because my given is grams, if you look at your map, it tells you to go from grams to moles out to molecules. To do that gram to mole part is what we've done already. You need a molar mass. Remember molar mass, we have our formula C12H22O11. We list out our elements. We have 12 carbons, 22 hydrogens, and 11 oxygen. Then you access your periodic table, look up each of their individual masses, rounding to 2 decimal places. Carbon is 12.01, hydrogen we use 1, and oxygen rounds to 16. We multiply and add that all up. We get an answer of 342.12. It's molar mass, so that is grams per mole. If you remember, that is a conversion factor. So I'm going to go ahead and take my given. That was the 4,536 grams. When we go to set this up, grams needs to cancel out. And so the mass, that 342.12 grams, will need to go in the bottom. That per mole is the top. So if you look at your roadmap, we have now gone to the middle. We've gone from mass to mole. We're not done. We need to go to representative particles. Atoms and molecules are the two types of representative particles that we're looking at in this class. So if you remember when we did conversions, you can add a second step. What I can do here is cross out grams, and I can see that I'm at moles. Again, what the problem asks us to find is molecules, so this is how I know that I'm not done. If you go to your roadmap, you see that moles is the middle. We're going to representative particles. Molecules, again, is a representative particle. So to get there, you use Avogadro's constant. Avogadro's constant is 6.022 times 10 to the 23rd. I'm going to go ahead and label this as molecules, but it can be atoms, is equal to 1 mole. Be careful with how you abbreviate molecules and mole, because that's easy to mix up, that's easy to flip it around and get an incorrect answer. That 1 mole, based on how my units are set up, moles is in the top, therefore moles needs to go in the bottom here to divide to cancel. That leaves me with the other component of 6.022 times 10 to the 23rd molecules or MQs. What you're looking for is moles and moles canceled, so all of my units eliminated. Now I can solve. There's 2 ways that you can go through and solve this. The first way is you're going to take 4,536 divided by 342.12. I would then hit enter, and then I would multiply by my 6.022 e to the 23rd. If you're still struggling with a calculator, please reach out to me. There's a few of you that I left comments for in your assignments that looks like the work's good, but answers are coming out a little bit off, and it might just be calculator. So please, if something wasn't right with those assignments earlier on, like worksheet A, let me know. We can talk and come up with a plan. So please take a second to run this through. And like I said, there's a second option. You can take 4,536 times Avogadro's constant, hit enter, then divide by 342.12. If you typed it incorrectly, you should get an answer of 7.98 times 10 to the 24, and that is MQs of sucrose. Okay, so again, your roadmap will help you guys out a lot as we get started with these conversions. So moving ahead, I've got one other example to take a look at today, and that's looking at aspirin. So aspirin is chemically C9H8O4. And so if you've ever had a fever or maybe had some kind of inflammation, you maybe have taken aspirin to relieve that. And so it wants to know how many grams are found in 1.67 times 10 to the 21st molecules of aspirin. Again, we don't have a direct relationship between molecules to grams. So if you follow your mole map, we're starting at representative particles because molecules is a form of a representative particle. We need to get to mass because mass is measured by grams. The only way to get there, according to our map, is you have to go through the mole. So the first thing that we need to do with our particular problem is take our given 1.67 times 10 to the 21st MQs. And if you follow your map, it tells you the only way to get there is to go through the mole. To get there, you're going to use Avogadro's constant. Because we are starting with molecules, molecules then needs to go in the bottom. So we're going to go ahead and put our 6.022 times 10 to the 23rd molecules. The other half of that conversion factor is 1 mole. Moving ahead, we are now at the center of our map. If you took a picture of that, if you want to pull that up, that'll help you understand what I'm referencing to. To get to the next part, we're trying to get to mass because we want an answer that's in the unit of grams. If you look, what we need to get from mole to mass is to use molar mass. So that's where I'm going to go ahead and take the minute to figure that out. So we have C9H8O4. So listing them out, we have 9 carbons, 8 hydrogens, and 4 oxygen. We just used these same 3 elements. Carbon was 12.01, hydrogen is 1, oxygen is 16. we can go ahead and multiply and add these three elements up. The molar mass I calculated came out to 180.09 gram a mole. So going back to my original calculation, I got molecules to cancel. I am now at the mole. As we make our way towards mass, I need my moles to cancel. So I'm going to take this part of the conversion factor and put that in the bottom. The top piece will be the mass, the 180.09 grams. Much like the last problem, you have two options on how to solve. You can divide first, so 1.67 times 10 to the 21st divided by Avogadro's constant. Hit enter, then multiply by 180.09. Or you can take 1.67 times 10 to the 21st, multiply by 180, hit enter, then divide by 6.022 times 10 to the 23rd. I would take a second, try this yourself, pause the video, and see how your answer compares. When you do this calculation and round it, I got an answer of 0.5 grams of aspirin. So a typical dose of aspirin is usually 500 milligrams or half a gram. So when you take that dosage, you are intaking 1.67 times 10 to the 21st molecules of aspirin. Okay, so these are the kind of two options that we have working through these conversions. Again, your roadmap will be really useful. You have 3 practice problems that I want you to work through. Again, you're going to upload this either as a digital example. You can take a photo and post it, or you can print it and take a picture and post it that way as well. Reach out to me with any questions or concerns. Otherwise, this is due tomorrow at 11:59.